Hello, everyone, and thanks to the Demuxed committee for accepting my talk around Playback on Edge. In case people are curious what Crunchyroll is or haven't heard of it, we're a top 10 SVOD service, quite a few subscribers, lots of users, many minutes streamed every month. Where did this project start? It came from the concept of sort of adding a lot more detailed telemetry to our player and sort of starting to discover a little bit more, getting finer grained visibility into what was going on. Naturally, we had sort of normal traditional QoE tools at the time: video start time, rebuffer rates, average bit rate consumed. There was lots of metrics that we were already gathering and taking a look at. But then as we took a look at the problem a little bit closer and started diving in, we came up with the concept of sort of these client-side rollups, which let us really increase the fidelity of the event volume that we were observing, and then sort of summarize it into a single event that we then sent out to our backend. This started to give us a lot more insight into some of the performance challenges we were facing. Just to visualize the client-side rollup concept, basically it's sort of an aggregation of all the elements of a video session into an event object that we're able to consume on our backend. Once we started looking at this data, unsurprisingly, global origin latency impacts playback performance globally. So we got a lot of more details. This is also during a time where Crunchyroll had an increased traffic load through international audience, and it really started to become very apparent that different aspects of our player build out were being impacted pretty negatively by having to come all the way back to our centralized origin location. Certainly we had already employed a multi-cdn strategy, so the segments were on edge, but the other pieces not so much. Here's to sort of summarize: resource APIs on origin, our VMAP SSAI XML was being hosted through a third party and sort of manually geo-provisioned in different regions, which gave us decent coverage, but not as fully localized as our global audience was. When you do a VMAP XML, SSAI needs to associate itself with a video sequence that also was similarly geo-dispersed. DRM token auth was taking place in largely on origin, and then a few more. And then our multi-cdn service was also partially geo-dispersed, and again, was running into different performance challenges relative to global reach. And then, of course, our actual video segments that I mentioned earlier, they were, in fact, part of a global multi-cdn strategy, and hence already fully globally dispersed. So, problem: how do we go from US West 2 to everywhere one step? Well, we don't. But I think this talk is a little bit about how serverless and edge distribution can really help you sort of leapfrog or get there a lot quicker than you otherwise could have relative to a medium-sized online video publisher's infrastructure outlay. So with these things, always important to plan big, but start small. We came up with the project concept of Katana, which was going to be our edge playback orchestration for stateless multi-cdn and SSAI. And so basically we observed that, aside from many of these services being not close to the user, there was a lot of back and forth between the player and these different services in order to build out a playback experience. And so, when we started formulating the concept of this project, we knew that we had to do more than just geo-disperse the services. We also had to look at avoiding round trips altogether. And to do that, we kind of borrowed some concepts from GraphQL, where you sort of communicate a resource graph or request graph that tells the server what all you need. And in the context of a user video playback session, this includes things like: can I play Dash? Can I play HLS? Can I play V1 or HVC? In our case, we have soft subs versus hard subs, and different players can support one or the other. Certainly in the case of server-side ad insertion, you're passing a lot of parameters relative to the metadata of the video, the user ad ID and so forth. The concept that we wanted to explore with this project was, could we resolve this in a single round trip? So, give me the dash resource stitched with ads along with the associated VMAP and so forth. What does that look like? In this case, our API was pretty simple. We just extended the resource list with an embed associated object that had the payloads of the respective resources. This gives us a condensed request flow, sort of combining a lot of different resources into a single edge response. So we had the plan, looked good. We started to explore solutions in the space and started building. The first service that we tackled was the manifest level multi-cdn. This was a service that basically handles giving out different CDNs in order to our users based on some different data, like what sort of ASN they're coming from, what geography they're coming from. In the near future, we hope to incorporate more robust performance data as opposed to sort of some of the manual tuning that we do today. But basically, the concept is, manifest represents the different CDNs in order of preference, and the players can play it. There's a few nice things about doing it as a spec. You can kind of quickly get it rolled out to a lot of different contexts. Our URLs are tokenized, so we have to concatenate the tokens together. Credit to Jeremy Brown on the Dash Slack channel there had that idea. And similarly, HLS has a spec that different renditions should be supported. And so it was pretty straightforward to add it for the HLS-based streams. Some other things to keep in mind with multi-cdn manifest manipulation: we wanted it to be very quick. The edge region decisioning, so there was no phoning home in order to construct the ordered list of CDNs. The manifest level is not constrained by player integrations, as we mentioned. That was a good first project for this Lambda effort, so we could roll it out pretty aggressively across the entirety of our service. What's important here, the server is just supplying the recommended order. Players can negotiate on top of it, and we have some projects or we're starting projects to explore getting the player involved in making congestion failovers so that the ABR algorithms can be extended to support even better delivery relative to the CDN list that is provided. The rules engine today, as we mentioned, a few different parameters that feed into that. And then I think another neat approach that we took here was doing sort of module content hash, where there was just sort of a business rule level decision, allowing sort of URL affinity to give CDNs a fair cache hit ratio when doing delivery. We rolled that out. We got some significant performance gains, especially globally, where the performance grew the greatest relative to sort of the partial geodispersity of our previous manifest serving solution. Next up, we were looking at server-side ad insertion. The basic construct around server-side ad insertion: you have this service, this Edge Lambda service. It's going to hit your ad network. That's going to return back a VMAP XML document. And from there, we're going to construct a new VMAP document that has reference to content that has been ingested into our system. And that basically works by just checking for that key by sort of deterministic hashing of the ad URL, and is able to quickly sequence in the content, look up the durations, and represent it in the XML. If it's not available, we get a 404, or we fail over, then we trigger the ingest flow through an SNS-based queue system. Some stuff that we were aiming for with the SSAI solution, want to, again, make it as fast as possible. And then, as I mentioned, do the deterministic hashing of the ad stream URL. Again, this enables sort of full resolution of a VMAP and sequenced
multi-period dash or sequenced discontinuity HLS, all within a single edge node, right? Like as we'll see later on in the presentation, the enemy of performance here is having to travel for the data. It combined with the same manifest manipulation system that we were using in the first project of the multi-cdn implementation, which meant that the same multi-cdn strategy could be respected across our AVOD and SVOD delivery, better cache hit rate, all that good stuff. The ads were ingested with the same engine as our content. So again, we get very closely aligned profile, which is important for SSAI consistency of stream experience. And then it was fully RESTful, right? So, like as we mentioned in the clever acronym name of the project, it's stateless. The respective URLs that are consumed for both the sequencing and other elements are evaluatable from an arbitrary endpoint. And this combined for significant performance gains over baseline. To go back to sort of like where we chose to do this, we were looking at a few different edge solutions. There's increasingly a lot of options available, including Fastly and Limelight and a few others. We were looking at Lambda at Edge just because, well, it has its own positive qualities and also integrated very seamlessly into our existing AWS infrastructure as code paradigm. Some things to keep in mind, though, with Lambda at Edge, it's not true edge. It's just actually replicated into all AWS regions, which in practice gives you much lower global latency than sort of a manually globally dispersed infrastructure provisioning approach. Lambdas are not destroyed. This is an important quality, which helps performance. We'll talk about that a little bit more shortly. There's no shared cache, so you can't, there's no like Redis or Elastic Cache or anything within that you can use to store resources across requests, but you can use CloudFront as your second cache tier, in addition to an in-memory cache relative to the Lambdas not being destroyed after their execution. CloudWatch is your friend. We'll talk a little bit about that. And then, of course, JavaScript is, hopefully you like JavaScript if you're going with Edge Lambda at present. They don't support all the languages that they support in the origin lambdas, if you will. Important to understand about the platform that you're developing for. So certainly serverless, has great qualities in that you're able to quickly get up and running and run your code. But if you're pursuing a project at this scale with hundreds of millions of invocations per month and billions of minutes served, you kind of want to dig a little bit deeper and sort of understand how the system works. Basically, there's sort of some micro VMs that are provisioned and run the respective code. The auto scaling structure for serverless is essentially provisions. There's this cold start penalty that they refer to, which is provisioning that micro VM and establishing it. Takes a few hundred milliseconds, and then once it's established, it'll just execute in sequence as requests come in. But the nice quality of Lambdas is that it sort of has that very fixed resource allocation that doesn't fluctuate. So in other words, one of these micro VMs is going to handle one request at a time in sequence, and so there's no variance introduced outside of the fact that you're in JavaScript and other unpredictable things happen. But in terms of the VM allocation, it's fairly predictable, and that's a useful thing to understand. You are running on the same physical hardware as other instances of these lambdas, and so it may be related to that, maybe just related to JavaScript, JVM, and other elements at play. There's not as fine-grained predictability about the runtime of your application. Getting into sort of the application architecture and kind of caching in the right places. As we mentioned earlier, these little VMs are long-running. They can run for up to, I've seen many hours of a single, as long as you're continuously requesting against the service. you'll see lambdas run for a few hours normally. Because they run for a few hours, because you need to provision 1024 megs of memory to get a reasonable compute envelope, you can use this memory to run a in-memory cache on the respective lambda. This facilitates great performance when trying to, service some of these endpoints very quickly, which is how we got to the point of 10 millisecond runtime that we were seeing earlier. Is really sort of leveraging this technique, because we're able to, have a fully formed dash object already parsed and ready to go in JavaScript serialized memory format, and then just sort of do presentation level manipulations as needed, and send it out to the client with very low latency as you're just reading an in-memory object. Where you do not have your dash document in memory, then you want to fail over to a second tier of cache. In this case, CloudFront is well suited. You can get very low latency. I have 5 written here, but I've seen less than that, 3 or 2.9 milliseconds of latency between the Edge Lambda and the CloudFront cache, the nearest CloudFront cache tier. Then if it fails to hit the CloudFront cache, then yes, you're failing back to wherever your video objects or video documents are stored. That could be your, in our case, it's a just-in-time packager origin out of US West, pulling from the fragmented V4s and creating a dash document or the individual segments in the case of the actual video delivery. So just to zero in on that concept of presentation level transforms, another sort of performance trick here is to return the object directly. This, kind of an anti-pattern in cache management, but very helpful in the case of trying to keep the overall runtime of your Lambda underneath that, 50 millisecond threshold that then occurs a second allocation of cost. Going back to sort of how the overall software structure is within the project, we don't want to sort of jump around too much when servicing a request. So that means that we kind of collapse, not only are we collapsing the end user client request into a single round trip, we're also collapsing everything that's happening in the Lambda into a single execution runtime. This has a lot of benefits as we look at sort of object cache reuse within the runtime itself. So we're able to, use that same dash object to construct the frame accurate timings in the VMAP XML document representation, as we are able to use for the export of the manifest itself into the more multi-period dash sequenced stream. So the basic structure of the application is a bunch of lambdas that sort of recursively call into themselves for the aggregation. We leverage the same AWS constructs around event handlers in order to facilitate this, so that if in the future we break these routes off into their own lambdas, or we do other optimizations or cleanup, we can retain that flexibility of direct invocation. Another important aspect of all this, you want to score everything within the Lambda ecosystem. We sort of just output some JSON objects to a log. These are fairly verbose JSON objects, can be up to a few K of JSON. And it has basically every, very detailed profiling of every network resource that was requested, how long it took, what the XML parse time was for the resource, as well as sort of application KPIs, whether we were filling paid ads versus house ads, and what within the multi-cdn resolver, what CDN did we choose and why, the total runtime of the application, and so forth. All these metrics fairly straightforward to just plop into CloudWatch graphs, which we've been able to do and get up and running pretty quickly. though certainly you can set up some tooling to connect it into your Datadog or New Relic if that's your central observability platform of choice. What's next? I think we're trying to get that GraphQL-like resource aggregation component fully rolled out. We want to enhance player-level negotiation on top of the server-based multi-CDN recommendations, and certainly want to open source any components of this that would be useful for other folks to take a look at. And thank you for listening, and of course, thank you to the whole team that worked on this project, from the video infrastructure group and from product and QA and everyone else at Crunchyroll. And hand it off to the next speaker. I guess we'll do some questions and then we'll hand it off to the next speaker. So thank you so much.